do this. My name's Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub here at MIT. And what I'm going to be talking to you about is some of our research about streamlined life cycle assessment for buildings. And I'm presenting this, but we have many people who have worked on this on our research team over the years, and I'll be pointing some of them out as we go along. But a big motivation for us to get into this research is because there's a lot of talk about green buildings. Everyone's really interested in green buildings. This is a chart from a study done by McGraw-Hill Construction talking about the U.S. single-family housing green market and how much it's increasing. And we see similar things for LEED-related construction. This is from the U.S. Green Building Council. And in fact, you know, they claim that the green building industry is growing faster than the non-green construction. And what's interesting, when you look back at the McGraw-Hill Construction, when they ask about what are drivers for green buildings, you know, most of it is that clients are asking for it. And so certainly we think that's a great thing that people are asking for it. But of course, they all say they want a green building, but it still leaves this question about what does it mean to be green? And, you know, the best way to really be quantitative about that is to take a life cycle perspective for any claim about greenness. And the reality is that there's many mechanisms for reducing environmental impact and cost. And when we take that life cycle perspective, we see that, right? Like in the materials that are used in the building, you can use recycled content to reduce the energy consumption that's required to make those materials. But of course, you can also design the building to use less material or design it to last longer, and that can also be something that can reduce the environmental impacts and costs. Of course, during the use phase, if you can make it so that it reduces energy consumption, that can have benefits, and anything we can do at end of life to enable material recovery is also going to be beneficial. But the trick is that if we're going to prioritize these different mechanisms, they require a trade-off analysis of really how these things affect performance and life cycle environmental impacts and costs. And that's because any decision is going to really be about those trade-offs, right? We have certain performance or functional requirements that we expect from a building, and those are going to have cost implication and environmental impacts. And so the importance is to look at all those things together. Now, so what I'm going to be talking about today is really these environmental impacts and how you quantify those from a life cycle perspective, and in particular using a life cycle assessment, which is an approach that you can use to be able to do that. So here at the Concrete Sustainability Hub, we've had a portfolio of different research topics, and some of these I touched upon in a webinar a few months ago when I was giving an overview of our LCA research, so I won't go into detail on all of those. You can find that webinar on our webinar website. But broadly, what we've been doing in this research is trying to identify what are some of the key drivers of building environmental impacts. Also assessing the state of LCA in the building design process. And third, supporting early stage building design decisions with quantitative life cycle environmental impacts. So that's what we've been trying to do. Our approach basically for the first one was to conduct some detailed LCAs, which we did several years ago, and I went over some of those results in the previous webinar and are available on our website. In the second one, we did sort of a broad review of the state of LCA, and then from that, we've been developing some streamlined life cycle assessment tools. So what I want to do today is just kind of go over a little bit of what are some of the key results coming out of our assessment of the state of LCA and how it's being used in the building design process, because it's important how that laid the foundation for the streamlined life cycle assessment work. And really what we found is that there's this chasm between quantifiable green building tools on the one hand and literature, and then designers on the other. That is, that basically there's quite a broad set of literature that's available and tools, and on the other hand we have architects, builders, developers, and consumers. And at least, the majority of the people that we survey don't use LCA tools. Of course, many are modeling energy usage, but that's not the same thing. So what we're trying to do with our research is to bridge this chasm, to try to bring those two sides together. And one of the ways that we did that was to try to do some surveys and focus groups with the architecture community to try to understand this better. And so we spent some time, we surveyed some architectural firms and conducted some focus groups with Boston area architects. So by no means do we consider this to be a statistically significant sample, but I think we had some interesting insights nonetheless, and there's a HTML reference down here that's on our website about where you can find a report that describes this in more detail. But basically, the discussions that we had were trying to get after when are design decisions made in the design process, which tools are used throughout the process, and what are the challenges to using LCA. One of the things that we found, which maybe isn't a big surprise, is that details aren't available until late in the design process. This chart here is showing basically what's the timing of detailed decision making on these different elements of buildings. So just an foundations, fenestration, exterior walls, interior walls, and floors. And what you can see based on the responses that we got, most of the detailed decisions occur later in that design process. Some of the other things we found is that, there was just limited demand for LCA from customers, and so that's why a lot of them weren't doing that. This was a few years ago, and maybe some of that has changed, but I think probably on the whole that's still true. The other thing, was just what I showed. The details aren't available until late in the design process. And the other barrier that we found to implementation of LCA was that LCAs are considered too costly and time-consuming. So this top one here about demand for LCAs, that may be changing based on what's going on in the industry. But for these other two, that's an area where streamlined life cycle assessment can really help and make a contribution by making it less time-consuming and also adapting it to the details that are available. Now, as many of you may know, a LEED has started to incorporate life cycle assessment into it, and in particular in these materials and resource credits, there are points that are available for environmental product declarations, which is basically like an LCA that's done for a particular building product, and then also what they call a whole building LCA. But what's interesting about those is that the LCAs that are in LEED have a limited scope, right? The environmental product declarations take up basically just cover what they call cradle to gate of those building products, right? The materials that are used to make it and then manufacture those, but it doesn't include construction. What they call whole building LCA is really just of the embodied portion of the building, right? Just the materials that go into that. And so that, once again, just includes the materials, the construction on site. It can include end of life, but it misses out on sort of that occupancy and maintenance. And, a lot of research has shown that for most buildings, most of the footprint actually happens in this occupancy and maintenance phase. So there certainly are some more high performance buildings where that dynamic is shifting, but for the vast majority, it's going to happen here. So this is basically, led us to conduct this research on early stage building design decisions that are still quantitative using life cycle environmental impacts. So There's a couple different challenges of supporting design decisions using this quantitative information, and they're related to a couple different tensions in the design process, right? One of them is that we need guidance early on, but that's also when we have the most uncertainty in the design, right? So if we look at our design process starting early with planning and pre-design and then going all the way to construction documents, as we know, the most ability that we have to influence performance happens very early on in that design process and decreases over time. And a big part of that is because there's significant costs associated with making those changes, right? So changes happen later on in the design. So, but what's interesting is that most LCA that's done actually happens pretty late in the design process, and that's kind of out of necessity because that's when a lot of the information that's needed to do the LCA is available. So what we'd like to do is to have streamlined life cycle assessment that can be used earlier on in the design phase. But of course, that comes along with this challenge that that's when we have the most design uncertainty, right? So that's one of the tensions that we're dealing with. The other one is that we want to provide guidance on design decisions. However, we realize that it's important to maintain design flexibility. Kind of going back to my triangle early on that I mentioned of this, we want to be able to balance performance, cost, and environmental impacts. And in particular, when we're at that early design phase, we're really experimenting with many different solutions, and it's because we have a whole bunch of different objectives, right? We're trying to manage safety, resilience, whatever, daylighting, acoustics, the aesthetics. There are many, many different things that designers are trying to balance, and if you're trying to find the lowest environmental impact and cost solution, the reality is it's hard to account for all of those together, right? So we don't want something that's just a pure optimization exercise because that actually overly constrains this performance process. So instead, we want to be able to provide guidance, but we want to look at kind of near optimal region of the design space, okay? And so we have that balance between flexible versus critical aspects of the design. The other challenge about being quantitative about life cycle environmental impacts is that we have this tension in life cycle assessment between cost and credibility. And basically what I mean by that is that generally what we associate with LCA and what we heard from a lot of architects is that there is a high cost associated with it. But that's because it's under such scrutiny, people do that in order to get high credibility. So if we look at sort of the conventional approach for doing building life cycle assessment, it is a high cost and high credibility model. And basically what happens is that we require what we call a bill of activities. So this includes the bill of materials, which would say how much mass of the materials go in, and also but how much energy is used in the building. Then we multiply that times impact factors that we get, which are used in life cycle assessment. What's the global warming potential of materials, or maybe ozone depletion of an activity. And from that, then we get our various environmental impacts. And a key thing about the conventional model is also just that the energy and embodied impacts are analyzed separately. And that's generally just because that's how these things have evolved, right? That we have energy analysts who do the energy analysis, and then LCA experts do the embodied. But a key component of this and a big challenge is that we have to get from a description of the building that architects are using and translate that into a bill of activities, which they're generally not working with. And so that's a big challenge associated with it. Now, we contrast this with what a streamlined building life cycle assessment model, and in that we're trying to reduce the cost while maintaining the credibility. And what we've called this is the Building Attribute to Impact Algorithm, or BHIA. And the reason is that we take the attributes, we take a description of the building, and then translate that into what's needed And also, importantly, we analyze the energy and embodied impacts together. Because obviously changes in the materials affect the embodied impact, but also the energy consumption as well. And we do this using a couple different elements. One is what we call attribute to activity models. So we have models that basically map whatever attributes the designer is working with into the information that we need with the LCA. So that can be about materials, processes, and energy impacts. Another key element of what we do is called under-specification. And with this, we use low fidelity and high uncertainty data. And by low fidelity, we just mean it's rather broad categories. But by consequence with that, we can capture the uncertainty with it. And last, we make use of what we call probabilistic triage. Probabilistic means it includes that uncertainty, and triage means we're trying to figure out what's the key data that you would want to go after, and thereby, limit the amount of effort you have to put on this. And the approach is actually, it's basically an approach where basically you start with underspecified design information. Oops, that didn't work. There we go. And we run some Monte Carlo simulations, and what that means is basically we're capturing the uncertainty in the input data and then running a whole bunch of different scenarios accounting for that uncertainty, and then we quantify the embodied impacts of buildings, the use phase impacts of buildings, and then look at the total. Now, the triage element is that from that analysis, we then are able to understand what are the key parameters that the designer is working with, the key attributes that are affecting this result the most. And then what we can do is specify some of those further, only go after those top few ones, and then run the analysis again, and then keep that going until basically we have a result that we're satisfied with. So once again, what we're trying to do with this streamlined approach is to get low cost and high credibility. And part of the way we do that low cost is basically by just having less detail that's required in the life cycle assessment. So in a conventional life cycle assessment, you need a lot of detailed information, whereas in BHIA, it's really something that can be just kind of approximate dimensions, approximate parameters, and then so you're using everything kind of rough. And even if you don't even know what kind of wall type you have, that's fine, because that can be underspecified, and you can keep in that whole range. So what are some of the benefits of this approach? So the building design attributes are inputs. You don't have to put in inputs of total amounts of material or anything like that. We do combined embodied and energy analyses, which are really critical to considering that whole life cycle environmental impact. You get feedback on what are the key parameters in the analysis, so you only need to spend time on what's important, and thereby you only need to specify the details when necessary. And you're also quantifying the uncertainty, which is really important for an analysis like this, where there are a lot of uncertain elements, particularly early in that design process. So what I'm going to do is give you an overview of basically how this model works, and basically diving into each one of them. And I'm going to start with these attribute to activity models, which help us map these building attributes into bill of activities. And that's one of the key things that allows this to be streamlined. And basically what it is that we start with user inputs, about what the geometry is, what kind of wall systems are being considered, what are the attributes of the attic, roof, and things like that. And then we have a couple different attribute to activity models. One is about use phase energy, and then one is about the materials in the building. And so basically what we do, like for example with the use phase energy, we use all those attributes, we put them into our AAM model for energy, and then from that we can get a use phase energy. And then we do a similar thing with materials, where basically we take those attributes and we use them to determine what kind of materials are actually used in the buildings. So let me give you an example of how we developed a use phase energy attribute to activity model. And essentially what it is, it's a statistical regression model relating the building attributes to predicted energy consumption. So what we do is we basically define a scope for a type of buildings. And right now we've done this as single family residential. And so basically we take the attributes of thousands of different designs and then run those in an energy model software, Energy Plus, and then get a bunch of results and then use those results in order to basically calculate what's the predicted energy consumption in each design. And this statistical model is much quicker than having to run one of these every single time. So although it's not perfect, as we've said, we're in early design decisions, and so we don't really need precision at that point. And also we're capturing the uncertainty in these calculations based on the statistical regression model. When it comes to the materials attribute to activity model, because we're also looking at single-family homes, what we can do is basically, based on whatever geometry is defined, we can then calculate the amount of materials that are required. And so, but when we know the assembly areas, we can determine the amount of materials within each assembly. So that requires some calculations, but is pretty straightforward, as we said, for single-family homes, and even probably for like low to mid-rise building structures as well. We can do that. I'll talk a little bit later how this will change for larger, more complex buildings. All right, so that's the attribute to activity models. The next topic is this under specification, which is a key part of being able to use this early on in the design process. And so this involves low fidelity and high uncertainty data. Now, let me talk about what I mean by that. Essentially, what we have different levels at which certain parameters can be described. So this here is showing insulation, and the L1, L2, and L3 basically are about which level of specification that you can use. So for example, in the analysis, you can start out by just saying, I don't even know what kind of insulation I'm going to use. Let's just say it's any kind of insulation. Or you can specify something and say, I know it's going to be fiberglass. So you can specify at that level. Or I know it's going to be glass wool, or I know it's going to be natural. So you can choose one of those. Or, alternatively, you can say, I know exactly what kind of insulation I'm going to use, and you can make a selection here at level 3. The key thing is that basically, the lower the level, the L1, that's the more variation that you have. If you specify this right here, the model does that's fine, but it captures basically the impacts of every kind of insulation in this category, right? And so as you go down here, it means you have more detail, but there's some additional cost required with basically specifying or making the decision about this more detailed approach. So we can do this for products or materials that are used, but we can also do it with elements of the design as well, right? So this is showing an example of roof pitch. You can just say, I want it to be any roof pitch possible, or it can be for a moderate roof pitch, a steep, or a very steep, right? Or you can be really specific about exactly which kind of pitch that you're talking about. So just to summarize, we can specify these things at the building level, which talks about how much of the building we're talking about, at the assembly level, which means of which particular assemblies, and then at the materials level, which particular materials. Let me give you an example. When we're talking about the geometry of the building level 1, the most underspecified would be any size house. So we basically have sampled, we've taken statistical data on what are the sizes of houses within the U.S. to give us a range. But then we can be a little bit more specific and say we know it's going to be a medium size or a smaller medium size. So the most specific would be here's what the square footage is. And even at that most specific, we include a little bit of uncertainty. Similarly, another building parameter would be a property of the building, and a key one that obviously relates to energy consumption is how much air leakage there is. So we can say there's any level of air leakage, we can say it's low, or we can give a specific number on that air leakage. When it comes to assembly levels, you know, we can, for example, here's an insulated concrete form. We can do a similar thing where we can talk about specific assemblies, and then, but the materials within those assemblies can also be underspecified. We can talk about rigid insulation, expanded polystyrene, foam slabs. So we have a bunch of different options within there. And the good thing is this allows for a lot of flexibility. As I mentioned early in the design process, if you haven't decided on any of these things, you can leave everything the most underspecified. However, if you have made some decisions early on, you have that flexibility. And so that's the key for us to be able to maintain that. All right, the last step in BHIA is this probabilistic triage. And this is really important for it to be streamlined because what we're doing is identifying really important attributes. And basically, after we run it once, we get a ranking of what are the key parameters that are really driving this analysis. So, for example, you know, when we do the analysis, this tells us that what kind of roof deck you're using and the roof and attic is really important, as is the attic insulation. Then comes the windows, and then a whole bunch of things. Now, this here is showing the top 10, but as you can imagine, there's dozens of other ones that we're, you know, over 100 that we're not showing right here. The great thing is what that means is you don't need to spend time specifying those, because even if you did, it would have very little impact on the result. You should really focus on specifying these top ones here, because those are the ones that are going to have the most influence. So let me show you an example of how this could be used. You know, we assume that people are going to know where they're designing the building, so we choose a location, like let's say Phoenix. And generally, we also think that due to customer direction, we're going to have an idea of what the square footage of the building is. So if that's the only thing that we specify, just the square footage and that it's in Phoenix, and then we have a 6-year analysis period also that we're using, we can get a result for the environmental impacts of this building. This green shows the embodied part, the blue shows the use phase, and the red is the total. But as you can see, we also have these error bars on it as well, okay? So nothing else specified except for those two things. Now, the other thing that we get, though, is basically what are the key drivers of this analysis. And so probably at the building level, it's no big surprise that the efficiency of your cooling system is going to be a really big driver in Phoenix. The next thing that we see is the window-to-wall ratio, then which windows you're using, and then here's a couple other ones that we see here in the top 10, you know. But the exterior wall envelope in this case here, you know, is way down there, and so that's the first time we really, aside from the attic insulation, and actually, what these elements here are basically more related to the materials that we see in the embodied, but those are here because they have a big impact on the energy consumption. Now, what we can do, let's say we specify this further. Rather than just saying any cooling efficiency, now what we're going to specify is at that next level, building level 2, and now we specify it as a high-efficiency air conditioning system. We haven't even gotten into specifically what the details are, just said that it's high efficiency. Now we have a different ranking here for what's really a key driver. And so the next one here is what's the window-to-wall ratio. So it's interesting, the cooling efficiency is actually still a really big driver here, but now it's the third element because we've specified it, so we've reduced that uncertainty. So let's say next we then decide to specify further the window-to-wall ratio. And what you can see here is basically how this reduces the uncertainty as we specify the top elements in each step, right? First we started with the high-efficiency air conditioner. Now this is about the windows and the window-to-wall ratio. This is about what kind of insulation we're using, roof, etc. So all of these things. Now this is the highly specified result here. Basically, what if we, you know, skipped over a whole bunch of steps here? That's what the ... is. And then basically specified that further. you can see that that's what the final result would be. It could be, though, that just after a few of these steps, you have sufficient information in order to be able to make a decision. And that's kind of the key elements. You only need to specify a few of these things in order to reach that point. So once again, let's go back to this comparison between conventional life cycle assessment and the building attribute to impact algorithm. For a conventional approach, you need a high level of detail, whereas for BHIA, you need a minimal level of detail. In a conventional LCA, you need a lot of design details, whereas in BHIA, we're talking more about design attributes that the architect is already working with. In conventional LCA, you need all the details, whereas in BHIA, you only need them when necessary. Conventional LCA is usually used late in the design process, whereas BHIA is used early in the design process. Usually, energy and embodied is analyzed separately, whereas we analyze them simultaneously. And of course, BHIA always includes uncertainty because that's a key element of what we're doing. So. We have a bunch of research right now on ways to expand this, and one of them I kind of alluded to early on is related how you use optimization of the environmental impacts and also costs using some artificial intelligence techniques. And the artificial intelligence is really the part that we use to do the optimization. And what we're trying to do is identify strategies that can be used to minimize impacts and costs while still maintaining that flexibility. So what this chart here is showing is basically some analyses where, as I mentioned, now we've also added on under specification of cost. And what we do is basically when we are running these analyses, we can look at a whole bunch of different scenarios because we have this streamlined and really efficient approach. What you see is that the red is kind of the initial populations of how it's looking at trying different building designs. And each dot represents a distinct building design that's being sampled. The artificial intelligence techniques, in particular, the one reason is a genetic algorithm, which is basically kind of inspired by looking at different generations and how they evolve, just like what happens in natural selection. And so what we see, the darker colors are basically as the algorithm is getting smarter and smarter and figuring out what are going to be some of the optimized designs, we can see right here is how much more efficient this final population is. Now, what we're trying to really wrestle with is kind of going back to that, how much that tension between optimization compared to flexibility. And so we're running some analyses now to try to look at what are some of those key drivers of what we call quasi-optimal building designs, right? It's not really that helpful to come up with the single best result because we may not, in our optimization, be accounting for all these different elements that are being considered. And so that's a big tension. The other thing that we're doing is, moving beyond this single family to looking at how we do integration of BHIA with more commercial design tools. And obviously, because for most buildings, there are designs that are happening electronically right away, and there's a lot of information that's already available. So how do we similarly balance the information that's available in that design process with what we need to do our analyses? And fortunately, there's already, a lot of information that's available, whether it be in BIM or other kinds of CAD software. And so we're looking at the best ways to do that kind of integration so that we can do more advanced types of buildings. So. All right, just some closing thoughts that I wanted to include here about, I think, why some of these streamlined LCA approaches can enable really the next generation of building life cycle assessment. And I think one of the things is that it really enables complete life cycle analyses, right? One of the barriers we have now to doing both energy and embodied, I think part of that is because of just how the architecture community is set up and that energy analyses are done separately. But part of it is because the challenge of doing those simultaneous embodied and energy analyses. So I think we've shown one approach that you can use to overcome that. I think one of the benefits, too, is that it can enable a more holistic approach to sustainability assessments, right? LEAD right now, essentially, they have a very good, whole life and whole building approach embedded within here, right? There's quite a few points available for energy analyses and points available for materials, but it doesn't really have a mechanism by which you can explicitly look at trade-offs within those, right? And so what an approach like this could do is say, let's more explicitly analyze some of these things using a whole building and whole life approach. And lastly, I think that what this can do is enable some of these questions to be asked early on in the design process, even when you have that high design uncertainty. So that's certainly something that we want to go after. So. Lastly, what I want to have on here is a list of some publications that'll probably be more for the academic community, but just to show you kind of the whole range of people that we've had working on this. We've had some collaborators in Italy who have helped us with kind of some of the more basic data related to the underspecification and the triage, and then a doctoral student, Josh Hester, who's really helped us piece this together. Some collaborators in Portugal who have applied this to retrofits. And then also some of our collaborators actually here at MIT and who are working with building design who are allowing us to test that. So, so this is something that, like I said, has really been a team effort, and I want to acknowledge all those contributions. If you weren't able to get a lot of that stuff, no problem. We have a lot of it information already set up on our website, which the link is right here, and so you can write that and you can follow up with questions there. And that's where we'll be posting in a few days recording of this as well. So in case you missed something or want to share it with someone else, you can go back. So. With that, I will stop, and then we can open it up to questions. And Anne, you, our moderator, is going to share those with me, and be glad to answer any that you have. And we'll, even if you are still typing it in, that's okay, because we'll be on here for a few more minutes. So.
Great, thank you, Jeremy. We did have one question come in relatively early in the presentation, and maybe a good opportunity to recap some of the conversation. But so the question is the streamlined approach specific to embodied carbon and carbon emissions? If specific to carbon, what is the potential for use in meeting code requirements?
So as you said, maybe it was something we addressed, but I'll still reiterate it. It's not just embodied. It is about embodied and energy consumption together, and it's not just for carbon or global warming potential. It's for multiple life cycle environmental impacts, which we see is, those are the types of impacts that they're looking for in LEAD and in other places. So it's not just for that. As far as meeting code requirements, I'm not familiar with any codes that would require analyses of a life cycle assessment in order to meet codes. However, there are increasingly green building rating standards that do have options for points that can be where you can use an approach like this in order to meet those. And so LEAD would be a good example, but also Living Building Challenge. And so they're increasingly having options where you can do life cycle assessments in order to get those points.
Thank you.
Yeah.
Excuse me. The next question is, will BHIA be open sourced or released to the general public? Also, what commercial design tools are you considering integration with?
So the short answer is that's definitely our intention, is to have it open source and available to the public. The bigger challenge when we do that, it's not so much, the challenge isn't the software itself, but the data that's used for the life cycle assessment. And so that's what we really need to work out before we make the whole thing open. Because, for example, we pay for licensing in order to be able to use some of the life cycle assessment background background data that's used, and the terms of those license agreements don't allow that to be just free and open. And so that's what we're kind of working through before we can make this available. And as for other commercial tools, we're looking at many that people use. Probably the two that we've been looking at closely so far are Revit and also Rhino. And as I said, what's interesting about looking at those tools is not so much just the tools themselves, but also it kind of becomes more a philosophical exercise of what is the design process and when are different tools used during that design process. And so we're trying to have some more discussions with architects about exactly those questions, and that should be able to help us better answer, which tools would be best to integrate with this type of approach.
Thank you. A follow-up question. What LCA background data sources do you use? Also, where do you get cost data? And then RS means is the next question.
Sure, yeah. In terms of data, one of the good things about using this under specification approach is you can take any and all data, and that's basically what we do. We have data from EcoInvent, we have data from Gabby, data from Athena, and we can sample from all of those. And the good thing is that even though they obviously have different background assumptions, for most of the different data that we're using, it doesn't really matter. And the good thing is that for the ones that it does, then we can kind of dive into those and get a better sense of if this really is a background database issue, then that allows us to be able to explore that. So the short answer to that is any and all. When it comes to costs, yes, for these single family homes, we have been using RS means for that data.
Thank you. Next question, does the streamlined approach capture the impact of reusing materials as opposed to using virgin materials or using materials with a high recycled content?
Yes, it can. And it basically comes into, let me go back to a particular slide where I talked a little bit about this approach right here. Basically, what it can be is that you can have material options in here at a very specific level that would say, here's the exact amount of recycled content that goes into that material, right? So, using concrete as an example, you can imagine there are many different mixtures you can use, some of which include supplementary cementitious materials and some of which don't. So if that becomes a big deal, then you can specify that, absolutely.
Thank you. We do have a little time left. That's all the questions I've received so far via chat, but hang out for just a couple of seconds to see if there's any more that come in.
Yeah, sure. Yeah, or even a couple of minutes. Still have time.
Couple minutes?
Yeah.
Absolutely.
Yeah. Maybe there was something else in that last question that I didn't quite get. It talks about reuse of materials. One thing we don't really have in there right now, at least, is how kind of reuse of new, or I guess reuse of old products, right? And that's kind of interesting question about how you set up the problem. But I mentioned here that some of our Portuguese colleagues, we've worked with them on this question about building retrofits. And so we're able to adapt the approach for that to that specific question. And you just end up just changing the scope of your analysis a little bit, right? You don't start from a brand new building. You say, here's already the building that we're starting with, and we're only examining the scope of the retrofit. So it certainly can be pretty easily adapted to something like that.
Great. And we did have a couple more come in. So
great.
The next question is, do you have an estimated timeline for when these tools will be available to the public?
I think we're looking at within a year. And like I said, most of it, the uncertainty around that just has to do with, if we can set up licensing agreements on the data. So that's what we're looking into.
Great. Another question about the tool. Are all of the simulation runs pre-computed beforehand and then we filter results from there, or computed in real time?
They are computed in real time, but it's pretty efficient, and that's all because of the way that we set up those attribute to activity models, right? They're just closed form solutions. There's no simulations or anything like that, so it's pretty efficient.
Great. And that's all the questions I have at the moment. Again, we can hang on if there's any more, but not seeing any just yet.
Okay. Great. All right. Well, if, like we said, if you do think of anything else, you can contact us here on our website or send us an email, and we'd be glad to follow up. Thanks so much, and
Great.
have a good day.
Thanks. Thanks, everyone, for attending.
Bye.
Bye-bye.